Good afternoon. Wow, was just lunch, huh? All the blood's in the stomach, nothing in the brain. It will get up there. Let's try again. Good afternoon. Okay, thank you. So today, or last time, in fact, since quite a while, we have talked about how we use a simple model, the Lewis dot model, and then expand it with some other theories, and we can go from 2 dimensions to 3 dimensions. And we have used the dot model, the Lewis model, and then combined it with another model, the valence shell electron pair repulsion model, a VSPR model, to look at a specific atom in a compound, in a molecule, and then see what kind of geometry that specific atom had, how this looks in 3 dimensions. And then you could look at the next one and do the same thing. At the next one, you do the same thing. And with this, you can get a 3-dimensional idea of a relatively complex model. So we have defined a steric number. This is the number of the bonded atoms, and the rule was there, we don't care if there's a single, double, or triple bond, it's just the bonded atoms. The single, double, and triple bond will get closer, of course. The distance between 2 atoms will be closer, and the bonding will get stronger, but nevertheless, it doesn't give you any idea or information how this is distributed in space. And so you look at the number of bonded atoms, and the number of the lone pairs. And each lone pair you count as 1 steric number. And with this, you get a steric number. If then you use that steric number, for example, 2, that would be, you could have a linear configuration. This is your central atom, and these are the atoms it's bound to. So these are 2 atoms. And so there's 1, 2, which would be steric number 2. That must be a linear molecule. Now, if you have 3 things bound to a central atom, 1, 2, 3, you would have the steric number 3, and with this you would have a trigonal plane. And you know also that the angle between each of them is 120 degrees. Nevertheless, you could have, and since we count free electron pairs as 1 steric number per free electron pair, you could have a free electron pair here, and then this would would be looking like bent. So what would be the angle around this about? It's still 120 degrees, okay? So if you have 3 things, if this has a steric number of 3, and you have only 2 things bound of this, you have here a free electron pair. Now, if you have steric number 4, you have a tetrahedral arrangement. This is your central atom, 1, 2, 3, 4. So that's the steric number 4. And if you have no free electron pairs, then you have the bond angle of a perfect tetrahedron, 109.5 degrees. However, if you have, for example, 1 free electron pair, this would like this. Suddenly it looks like a trigonal pyramid, because this one you don't see. You don't see the free electron pair. There's no bonding. So this would be gone. And with this, what kind of a bond angle would have? Remember, you have a free electron pair here. What would be the bond angle? You have the compression, the free electron pair compression, and the bond angle would be ammonia, bond angle, NH3. What's the tetrahedron, the bond angle? 109 degrees, okay? Now you compress it with 107 degrees, all right? Now you compress it with 2, okay? What would that be? For example, give me an example. Give me a molecule that has steric number 4 and has only 3 atoms. Water, H2O, okay? So we have 2, 1 free electron pair, and the other one. It looks to you like it's angular bent. So what's the angle between the 2 oxygens? 104.5 degrees. So there's more of that negative field pressing towards the electrons. The free electrons are pushing the angle together, all right? If you have steric number 5, you have 1, 2, 3, 4, 5 things coordinated to this. So you would have 5 is a trigonal bipyramidal. This would be if there's no free electron pairs. But the interesting thing is, if you would have one free electron pair, you could have a structure like this, a seesaw structure. Very funny looking structure, but you're going to do an example a little later. And if the second one is gone, okay, if the second one is gone, you could have a T-shape. For example, these two would be the free electrons pairs, one free electron pairs, two free electron pairs. You have those left, they would have a T-shape, all right? So this is a little bit tricky, so you have to really think hard how to do this, and don't doubt yourself, oh, I must have too many electrons, okay? The other thing is if you have steric number 6, that means you have 1, 2, 3, 4, 5, 6 bonds around the central atom. So you have an octahedral coordination. You can put an octahedron around it. You know that the angles are 90 degrees in this case. But if one is a free electron pair, let's see, this is a free electron pair here. So it would look like a square bipyramid, or a square pyramid, not a bipyramid, a square pyramid. This is the square, and these are the sides of the pyramid here. You have these sides, okay? Now, even a much trickier case if you have 2 free electron pairs. So this would be here, and this would be here. So it looks like a square planar configuration, and there would be no distortion due to because this pushes from this side and this pushes from that side, the free electron pair. With this, you wouldn't have any distortion, okay? So I gave you this, yes, it's in your handouts. That would be helpful, maybe probably also for homework and for the midterm. Now let's see if you understood, and I'm going to give you, this was the question where we stopped the last time. Yes, ma'am.
Can I ask a question about the 2 previous slides? So the molecular structure for one more. For that one, the C2. How do you
This here? Okay, you look at that central atom. You look for each central atom, you give it a steric number. So the question is, how do I know what the steric number is? So it's not the whole molecule is the steric number, it's each central atom. So what is this carbon? Has 1, 2, 3, 4. What is the steric number on this? 4. What's the coordination there? Tetrahedral. So one of the tetrahedron is bound there to the carbon. Now let's look at this baby here. What's the steric number on this one? Okay, tetrahedra. There's 2 tetrahedra which sort of touch each other on one side, on one point. So now let's look at that oxygen. What's the steric number here? It's also tetrahedral, okay? But you have 2 lone pairs. So that means it will look different, all right? Is it clear now? So you determine the steric number for each individual atom that's binding other atoms, okay? I think that was the question. So we have this SiH3 plus silicon hydride, and this is 3 plus, and then we have CCl3 minus. This is a minus here. So I want you to compare the bond angles. What you need to do, you need to draw your Lewis structure. First of all, you count how many total electrons you have. Then you draw the Lewis structures. Then you determine the steric number, and then with this you know the bond angle. And then you say the bond angle between the silicon and the hydrogen here, and here between the carbon and the chlorine. And you compare these 2 bond angles, and with this you can answer the question, is that bond angle between hydrogen and silicon, is it the same than here? Is this one smaller than this one, or is this one here larger than this one? Okay, why don't you think about it and give me your answer? I leave you this here on the other screen. You have a visual aid there. So the first thing is you think about the Lewis structure. You can't do it without the Lewis structure. Yes, you can actually. You can just guess, or you have done it so many times that you sort of see this immediately what it is. Just by counting electrons, you could see it. How come that so few come to my lecture? When Dellinger is teaching, 240 people show up. Huh? I'm getting jealous here. No, he's a great guy. Okay. So there is some kind of a majority, but a lot of people don't agree with this majority. So why don't you think about this again? Let's count the electrons here. So silicon has how many valence electrons? 4. It's in the third period, okay? So this is can be tricky. Not necessarily. And hydrogen has how many? 1, okay? Now so you have 3 and 4 is 7, so we have 6 electrons, okay? Because they are 1 plus. How many electrons you have for carbon? Carbon is the same, but it's in the second period. And how many for chlorine? Each of them 7. 3 times 7 is 21, plus 4 is 25, is that right? 3 times 7 is 21, plus 4 is 25, is 26 electrons. Okay, you need to distribute those around the carbon. That's the first step. Then you determine your bond, your steric number. This one you need to know, okay, what kind of shapes you have. You're not going to get this in the exam. You need to know what. Yes, ma'am. Switch it off. Switch it off, take the battery out. Sorry about this, but nothing I can do. I'll put it back in. I'll switch it on. How do you know it's not going to do it? If you click, what does it do? Oh, yeah, I click is bust, huh? There's no low battery. Did it fall? No. Did somebody stamp on it? Stomp on it? Sorry, I can't do anything. Warranty. That's strange. No, I can't give you any batteries or anything because then everybody wants them. No preferential treatment, unfortunately. I would like to give you all preferential treatment. Yes, there we go. Yes, all right. I don't know what helped, but maybe the majority helped. Did you discuss this with each other? So SiH3, we established already the silicon is 4 and hydrogen is 3, so it's 7 is 6 electrons. We have 2, 4, 6. Hydrogen has the duet rule fulfilled, but silicon doesn't, okay? Silicon is electron deficient. And carbon trichloride is 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and an extra pair. So what is the steric number for that? 3. So what's the shape? Trigonal planar, okay? Steric number 3, and the steric number is 4 here. You have to count that here. What's the shape of this? Tetrahedral, okay? So what's the angle here? And what's the angle here? 109.5. Oh, it may be a little smaller even because you have that free electron pair, 109.5, maybe 107. So which one is larger? So C must be the answer. Theta 1 is 120 degrees. 120. There you go. And this is 107. There it is, okay? This is the larger bond angle compared to this one. Good. Now, let's do another one. We have a molecule where X is iodine, bromine, or sulfur. And this has 2 chlorines on there. This has 2 fluorines on there. This is Y. And this has 2 hydrogen on there. Which of the following molecules are ions? This is a molecule. These are ions. Are linear or is linear? Sorry. So think about it, same spiel, okay? Good morning. Okay, so there is a slight majority for H2S. Okay, I'm asking which one has linear structure? H2S, how can that have linear structure? So there you have sulfur and you have 2 hydrogens. Okay, now what's the coordination on sulfur? Sulfur has 6, okay? All right, 6. And then you have the 2 hydrogen. This is 8, okay? So you have to do 8 electrons around it. So I can't help you at this. You need to think a little bit more. I gave you everything I could give you. Why don't you discuss this with each other? Just draw the Lewis dot structures. So the sulfur, you have 6 plus 1 each, so you can get an octet right there around the sulfur. Yes?
Can iodine have an extended octet?
Yes? 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 I didn't start? I'm so fascinated by you that I didn't start, huh? That's terrible. Why don't I give it a little less time than here? Because I have a lot to talk to you about today. Discuss with each other. It's a funny looking molecule. Very funny looking molecule. The one you expect the least is the one for this linear. Just, wow, we're inching towards the left side here, towards A, which is the right answer, A. And it's hard to believe that it's the right answer. But I show you why. Okay? So you have what you have, the Lewis dot structure. Sulfur is 6 and hydrogen is one each, so you have 2, 4, 6, 8. Duet rule fulfilled for hydrogen, octet rule fulfilled for sulfur. That means you have 2 free electron pairs. What's the steric number for that? 4. How does it look like? Tetrahedral. And what's the bond angle? You have 2 free electron pairs. 104.5, okay? Now the next one. So bromine has 7 and fluorine has 7. So we have, and then it's 1 plus 2, 4, 6, 8, 10, 12, 14, 16, 18, 19, 20. So 3 times 7 is 21. You have 1 left, so we have the right number of electrons. We have the octet rule fulfilled here, the octet rule fulfilled here, and what's the structure? What's the steric number? 4. How does it look like? Tetrahedral. What's the bond angle? 104.5, okay? So, and now this one is the real kicker here. You have iodine has 7, and chlorine has 7 valence electrons. So you have 3 times 7 is 21, plus 1 extra 1 is 22. So you got to arrange these 22 here. So you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. You have 3 free electron pairs. 3 electron pairs. So what's the steric number? 5, okay. And so if the steric number is 5 here, so where would the free electron pair sit? They would sit here in the equatorial plane, 1 here, 1 here, 1 here, and with this you have a linear molecule. Yes, you have a linear. There's 1 here, 1 here, and 1 there. I show you here, okay? Steric number 4, steric number 5, VSBR arrangement. This is now a tetrahedron for both of them. And this is a trigonal bipyramid. So this is flat here, this is the plane, the trigonal plane, and that's the bipyramid here. 1 here and 1 here, okay? So now, let's see. The bond angle here is, see that? So there's 2 free electron pairs. So this is how, there's 1 free electron pair, no, 2 actually. This is how it looks like. And it's bent, and it's about 104 degrees. And now let's go this one. We put this free electron pair here, this one here, this one here, and with this, we get something like this. It's linear 180 degrees, all right? That's a difficult one. So the answer was A. You need to practice this. I guarantee you there will be one in the midterm. Today, for the rest of the hour or the lecture, we're going to talk about isomers and polymerization. First, let's start with polymerization. If you have polymerization, you have 2 or more individual molecules that arrange each other to very long chains. So one of them would be called A and one B. So there's then A reacts with B, and then with A, and with B, and with A, and with B, till it forms a polymeric chain, a very, very long chain, a very huge molecule, okay? So one of those molecules is hexamethylene diamine. I have sort of put this as a cartoon here. What is the steric number on this nitrogen here? 4, okay. Why? Nitrogen has how many electrons? 5, okay. So we have, and hydrogen has 1, and the carbon shares 1. So you have a free electron pair, so that's a tetrahedron then, okay? What's the CH2? So C has 1 H here, 1 H here, the nitrogen here, for example, and then there's another carbon. What's the steric number on that carbon? 4, tetrahedral, excellent. And so on. So this is a tetrahedral. Each of them has a tetrahedral orientation, okay? That's how it happens. And so then we have sebacylchloride. Sebacylchloride, I made a cartoon that looks like this, okay? So that has the COCl group here. So what's the steric number on that carbon here? Can you hear me well in the back there? Yeah, steric number on the carbon is what? 1, 2, 3. Okay, what's the coordination then? How does it look in 3-dimensional? What is the 3? Good, exactly. Planar, okay? Good. All right, so that's not tetrahedral, okay? So now we want to react this with each other. And then you form a polymer where this part reacts with this one, okay? There's then a CN bond there, all right? That will change the coordination. Now, if you react this with each other, you get something like this. You get a polymer. And in our body, molecules are synthesized. Proteins are synthesized. These are essentially polymers. These are very long molecules, long chains. They are synthesized, for example, from amino acids, okay? And so I want to show you now a polymerization reaction. Polymerization is nothing else but putting molecules together to form a long chain. And so we have here once in the one bottle, Karen has, very nice, here a little sharp, and then we're getting there. Excellent, excellent. So what did you put in there first now? Sebasoyl chloride. Sebasoyl chloride you put in first, and now what's the second one? You can guess? Diamine, okay. What is it? Hexamethyldiamine, okay. So these are they are dissolved, and they are two immiscible liquids, okay? And so how could that polymerize? It polymerizes where the liquids meet. That's where they are polymerizing at the interface, okay? So we could grab the interface. Let's see if we can see do you see the interface? And so if we go, we are on which camera? On this one here? No, we're on this one, okay? If you see that here, the interface? See that? Not very well. So why don't you pull some polymer off the interface? So we need a white chart now. Not too wide, but it should show me. So I am going to pull now a polymer. Okay? See that here? It's pretty sturdy, and I can do this until all the stuff is used up in there, until the two compounds are used up, and I make that polymer. I got to get it on that drum here. Okay. See how sturdy that is? And so you make, for example, nylon is a polymer, and you can make a polymer, and you make fibers out of it, and then you can do these fibers and spin them, okay, and weave them, and with this you have a very sturdy polymer. And so this is the polymerization to a organic polymer. Nylon, for example, is a polymer. You know, many of you use it, so you understand polymerization. Now let me ask you a question. If you could have the light down a little bit more. Thank you. If we have ethylene, this is ethylene. two C's, H4. C2H4 is ethylene, has a double bond, okay? And the double bond can fold out. Why don't we do that? I need a white chart, please, again, and I have U4 and U4 here, please. If you could come up and quickly, because I need to get going on this here. Yeah, come on out. Why don't you stand here and face each other, close to each other, okay, and hold hands. So here, this is the double bond, okay? So you are pretty lucky here today. And so hold hands. So you are now, what you are? Ethylene. So you guys here too. Okay? A little bit more backwards, a little bit more. Backwards. And I need to put you here. So we have 1, 2, 3, 4 molecules of ethylene. Why don't you polymerize? Move that bond here, and move that bond here, and you move over there, and you move over there. Now we have polymeric chain of polyethylene. Now you have changed your coordination number. You have changed the steric number now, okay? Because the double bond was only 1, steric number, and the single bond is different because you have now more hydrogen on it. Okay? Thank you very much. The polymerization demonstration. So here it is. This is the polyethylene. From ethylene, we make polyethylene. And I want to know from you the CH bond angle. That's the angle between this here, the C and the H, and C and the H here, the C and the H here. So there are two H's, of course. Does the bond angle increase when I do the polymerization, when I go from here to here? Does it stay the same? Or when I go from here to here, does it decrease? So now you have to count your electrons. You have to come up with your Lewis-Dot structure, and you have to look at the carbon steric number, and then you compare the two steric numbers. Somebody's thinking about you. So that should be easy. There's no trick in it. No free electron pairs. So what's the bond angle here? And here. So how many, what's the coordination? The steric number here? 3. Steric number here? Okay, that gives you the answer. Everybody's got to have it. Don't forget to click in there. Where's the person who always moans? I'm going to be moaning now here, okay. So the bond angle decreases. I agree with you. Is it decreasing? Yes, it is decreasing. Okay, why is that? That's what I'm going to explain to you now. Those of you who haven't gotten it yet. So this here is, what's the steric number 3? Steric number 3 is trigonal, planar. Yeah. This here, you go, there's one H here, and one carbon here, one carbon here. So this has 4 bonds, okay? Steric number 4. So this is 120 degrees, this is 109.5 degrees. There's no compression, okay? And with this you get ethylene is 120 degrees, and the carbon in polyethylene is 109 degrees, okay? So that looks like it's, so the difference is 120 compared to 109, the bond angle decreased, all right? So there are isomers. Isomers are molecules of the same formula. They have the same molecular mass, but they have a different arrangement of the atoms, okay? So this, for example, is a very delicious compound here. It's the product of fermentation in many alcoholic beverages. And it's called ethanol, okay? This has 1, 2, 3, 4, 5, 6 hydrogens, 1 oxygen, and 2 carbons. So this is C2OH6, okay? So that's an alcohol. But there's a structural isomer which has exactly the same molecular mass even, the same bonds molecular mass, but it's a totally different compound. This is called dimethyl ether. Any compound that's a carbon and oxygen and carbon, it's called an ether, dimethyl ether. This used to be, ethers were used for anesthesia. And when I was 10 years old, I had to have an appendectomy. Actually, they gave me something over my face, like a cloth, a mask, and then they were dripping ether on it. okay? And then you pass out. You actually get poisoned. And so it takes you forever. So I was at it takes you about 4 days to get rid of the poison, and then you start healing slowly because the body doesn't heal very well if you poison it. So that was the only time I was in an operation where they used ether. Then the technology was better, and we had all kinds of wonderful drugs. So nowadays, they give you drugs, they can put you out for 1 or 2 minutes. It's just marvelous. Especially feels good when they do something hard on you. So these are structural isomers. They are very dramatically different in their chemical behavior. Okay? So actually the ether is a diethyl, so you have a CH2, CH3, CH2, CH3 group. Diethyl ether is the one which used to be used. That's been invented in the 1800s somehow. And before this, they didn't use any anesthesia, so they made the people drunk or whatever. You see this in Western movies, when they amputate the leg or something. And the guy drinks whiskey and then bites on a piece of wood. Okay, tough guys. Okay, but there are more subtle isomers. For example, a stereoisomer. They are very subtle differences, and this would be, for example, dichloroethylene. This would be one form, has 2 chlorines, one on the carbon, has a double bond and 1 hydrogen in each carbon. This would be a trans compound from a cross, from the Latin. I think it's trans is from Latin. Yes, means a cross. And the other one would be a dichloroethylene. This would be the cis compound. You see that? It's still, the chlorine is on the carbon, and the chlorine is on the carbon, but they are now on the same side. So they are cis on the same side. In Latin means cis, okay? And so this is the cis orientation, this is the trans orientation. But you could also have a structural isomer to that. So the differences are not very significant, but there are differences in behavior. But the structural isomer would look like this. So there you have, suddenly the chlorines are both on one carbon and the hydrogen are on the other carbon. So that's a very, very different molecule. So the difference here are slight and subtle, and the differences here are dramatic. Okay. So if we could look, for example, at the magnetic momentum, this chlorine has the electronegativity going this way, this momentum goes there. So this cancels, there's no no momentum, no magnetic momentum. This one would have a magnetic momentum. The addition of these 2 vectors would give a magnetic momentum to this side, and the addition of these 2 vectors would also give a magnetic momentum. Okay? So you should be able to also see magnetic momenta and you probably use the electronegativity scale for that. So now I'm asking you, how many structural isomers? So that's a totally different structure. Same number of carbon, same number of hydrogen, no addition of double bonds, and no formation of rings. But you can have structural isomers for this pentane. 1, 2, 3, 4, 5 carbons. This is called pentane. And so you could also draw this linearly. Okay, this is just for fun here. We don't really know how it looks exactly. We do know, but I depict it like this. But you also could draw a chain. So think about it, how a structural isomer would look like. It has to be a different composition. And so you have 3. The choices are 3, 5, or 7 structural isomers. So, but you always have 12 hydrogens around and 5 carbons, and no addition of double bonds, no ring formation. Okay. Now, let's not fall for this one. If you have a chain here, let's see if I had this here, maybe here. Let's see, 1 second. That's not going to help you. If you could also draw this as a chain, and you draw this here, then the next one is here, the next one is here, the next one is here, the next one is here. So if you would have this here, and you draw this on top here, it still is one continuous chain. That's not an isomer, okay? You just lay it flat. That's not an isomer at all. There has to be a real structural difference. And so why don't you talk with each other about this and try to give me a revised answer, at least some of you, please. Yes, you are getting better, but my computer froze now. Can't believe this. I knew that there was something going on here. Now there it is, okay. So A is the right answer. Why is that? So this is this pentane. There's 3 H's here, 2 here, 2 here, 2 here, and 3 here, so there will be always 12, okay? So that's the chain. If you put this, for example, up here, you bend this around and put it up here, it's still one chain. It's not a different structure. Or you can put this one up here, or you can both of them, one up here, it's still one chain, okay? So a real structural isomer would be, if you take this and put it here, this one here, and put it here, that would be the isomer, okay? That would be one structure. There's another possibility. What's the third possibility? You take this one here and put it down here, okay? So this is the 3 structural isomers, all right? And they all have 12 hydrogen, okay? 4 times 3 is 12, 3, 6, 9, 12, and 12, okay? We didn't change the bonds, we didn't form a ring. And with this was the answer. So there is even a more subtle isomerism, and this is what our body is very receptive to, this subtle isomerism. These are called isomeric molecules that are really, they have a chiral center. And the chiral center means that it's this one molecule in the center, and it has 4 different things that can be atoms or can be also different groups, more larger other molecules. So this is the chiral center. And actually, the isomer of this is only the mirror image. Only the mirror image of this would be the isomer. Look at this. So if I take the mirror image, would be the isomer. If I could have the camera on me, please, and the mirror down here, because we're going to do this now. So yeah, that's good, excellent, very good. So I have here my molecule, you see that? My molecule, it is the chiral center, 1, 2, 3, 4 different things. And you see, that's the mirror image. That's the it only agrees with its mirror image. You cannot, if I take it out real, you could do this, for example. Watch very carefully. You take this up here, and then you have it, the mirror image. Okay? Did you see that? So that's the mirror image. Let's look. It is not, we can get two to match. If you look here at the magenta and at the green. Well, wait. They gave me the wrong one. Let's see. The magenta and the green. Yeah, that's right. The magenta and the green. No, it's the right one. The magenta and the green matches. You see that here? But the brown and the white, I never get to match. Okay? Only the mirror image will match. Now let's do the brown and the white. Let's match that here. Got to twist it a little bit. The brown and the white matches now, but the green doesn't match with green. It matches with magenta, and this one here again. So these are chiral molecules. And if you have both of them together, you have a mixture, a racemic mixture of two isomers that are chiral to each other. All right? So you have, if I have a regular molecule, that's no big deal. There's not a chiral center here. I have one, two, only three different things on it, not a chiral center. So I can match this very easily. You see that? Okay? This is not chiral. So the chirality is defined then as the mirror image. It's the only, it matches its mirror image, nothing else. And so there is a left form and a D form, an L and a D form. This means levar rotating and dexa rotating. You don't have to know that. Maybe you should, because if you're a microbiologist or biologist, if you become a doctor, this is what you really need to know. And that means left is levo and right is dextro. And this was discovered by by Pasteur. He used these compounds, and you separate them, and you shine light through one of the two chiral molecules of one of the two enantiomers. It rotates the light to the left, and the other one rotates the light to the right. And so this is how they distinguish between the L and the D form. And so you see here, hands are chiral. Our hands are chiral. See that? If I do that here, am I on the camera? Hello? Bigger. Thank you. Good. Now you see my hands, and these are chiral. I could do like this, but this is cheating, okay? This is chiral. We are all very chiral. So actually our body is chiral. We only accept chiral molecules. We are chiral. So the body, let me show you at the end a demonstration, if I can have the camera on the front here. Can you help me, please? So we do the handshake. So these are my receptors in your body. And here's a molecule. This one fits very well, okay? Now shake my hand now. So the body, I'm not recognizing this molecule because it has the wrong chirality. So this works fine. This is where you have to do like this. Then it would work, okay? But that's not a handshake. So, but this is a non-chiral hand. It goes like this or like this. So shake it, okay? Shake it with the other hand. So that's not our body. Our body recognizes chiral molecules and only one form of them, and we're going to talk about this the next time. Thank you.